So today we're gonna continue exploring the Ehrenfest theorem that was the last subject of the Monday's lecture, right? And we'll consider a few cases and we will see if we can get to the point where we can explain energy time uncertainty principle. That's one use of Ehrenfest theorem, which is something that usually is considered more advanced subject, but you will see that with Ehrenfest theorem, it's actually quite simple. Now, let me share the screen and we will start. So as you can see here, we will consider Ehrenfest theorem. And Ehrenfest theorem is once you have an observable A operator corresponding to the observable is A with the hat. So then if you are interested in expectation value of that observable, this is the usual kind of property that we always can have for any observable. Just to remind you, in quantum mechanics, we may deal with the situation where our wave function at some initial time is not an eigenfunction of the operator, but if you do the measurement multiple times for this particular wave function that you can prepare in multiple copies, then you get the expectation value of the observable. And what Ehrenfest theorem sort of allows us to do is to see how this expectation value will evolve in time, because the Ehrenfest theorem gives us the time derivative of that quantity, right? Now, we discuss actually I discussed what we're about to talk about in the lecture 12 on my previous lectures, which are on YouTube channel, right? Lecture 12, you could review that material. And let's just start. Then you could think of A as being a Hamiltonian or momentum or position, any property you like. We will at the end consider some interesting property that is related to chemical reaction. That's another interesting thing where Ehrenfest theorem can be used. But no matter what property you're considering, it has an operator, and we can, using Ehrenfest theorem, predict the time derivative of that. Now, there are interesting cases of conserving quantities, and that's where your stationary state, sorry, not your stationary state, but your expectation value doesn't change with time. So one particular case is when the time derivative stays 0, right? So then this could lead to the stationary quantity. And in order to have that, one of the simplest cases is if you look at this expression, one of the simplest case is to have, well, both terms, commutator and the time derivative with respect to time, right, in the operator itself to be 0. So this case is when HA is 0 and dA over dt is 0. So no time dependence in A, and A is commuting with H. So the obvious simple example of this case could be that A itself is just the H. And if A is H, that means that the observable The operator is like this, and the observable that we are finding is expectation value of the Hamiltonian, and that is usually called energy, right? Total energy of the system. Very important observable, but according to Ehrenfest expression IH bar, the time derivative of H will be just 0, if especially H is constant in time, so it depends on space only, right? And this is just following from Ehrenfest theorem. No matter what wave function is, wave function itself can change. As we saw in general, you can write the wave function as a linear combination of eigenstates of the Hamiltonian, and they will have some time dynamics. But that all won't matter because essentially this expectation value will always depend on the expectation value of the commutator with the Hamiltonian, right? So, and this is 0 in this case, and there is no time dynamics of the operator itself, right? So the operator Hamiltonian doesn't depend on time. Very simple case. Now we could also make something less trivial. Let's say if observable is something that's not H but commutes with H, what this could be is for the free space, the operator can be momentum, and then it's also going to be conserved because for the free space means no potential. The Hamiltonian in this case is just the kinetic energy, and the V of x is just simply 0 everywhere, right? So then P commutes with T, and again the P expectation value is state constants. Okay. More than that, in the case where the wave function is real, the expectation value of momentum is always 0. That you can check for yourself. So this constant is 0 if the function that we're dealing with is real. And in the free space, if you start with a real function, that just simply means the average momentum stays 0. Okay, that picture-wise would correspond to something that looks like this symmetrically, and so it's not really moving one way or another. It's rather will probably just disperse, right? And the average momentum will stay 0, even though there will be some movement left, right, but for the wave function absolute value. But there will be no overall movement of the that could result in a change of the momentum. Of course, you could start with a wave packet that moves one way, and then the average velocity or average momentum will stay constant according to Ehrenfest theorem because there's no potential. If you add the potential, things will change in different places of space accordingly. Now, second case, it turns out that the time derivative of the expectation value can be 0 even when A doesn't commute with H, because even when we have non-zero commutator, we know it from Ehrenfest theorem that this quantity depends not on the commutator only, but on the expectation value of the commutator, right? So the fact that if a commutator is 0, then surely expectation value is 0. But if the commutator is non-zero, doesn't mean that the expectation value cannot be zero. How is this happening? Well, it can be shown through the sort of a simple algebra. Like, let's assume that we are dealing with the eigenstate of the Hamiltonian, right? So subcase A, H psi equals E psi. So we have stationary state as our function. So then it's possible to show that psi HA psi is zero. And how do we show this? We just write down what this expectation value is. It's HA expectation value minus the other way, AH, right? And the H is a Hermitian operator, right? So it can be applied to this bra part and to the cat part, and everywhere it gives the same answer, right? So an energy is real. So we get E psi A psi from this, and minus E psi A psi from this, right? So these two are the same. Therefore, if you subtract them from each other, you get zero. Very simple. Now, you could also do the same thing for the situation where A psi equals to A psi, right? So when the psi is the eigenfunction of the A operator. Same logic, A is a Hermitian operator. Therefore, psi HA psi is just going to be treated slightly differently. We still write this as a psi HA psi minus psi AH psi, and then apply A here, apply A here, we'll get A psi H psi minus A psi H psi, right? So these two are the same, therefore it's zero. Great. So as you can see, for the situations where we have states that we start with are eigenstates of H or A, and again, A is not time-dependent property by itself, the operator, not the expectation value. Then we could say that the time derivative of A stays zero, according to Ehrenfest theorem. Now, this is all kind of a bit abstract. I guess the examples one can give here is the, say, the situation with particle in box, right? Because for particle in the box, the only, I guess, observable that commutes with the Hamiltonian was Hamiltonian itself. It wasn't easy to come up with the observable like position or momentum. They don't commute with Hamiltonian. Position is just because there is a kinetic energy, and T doesn't commute with H, with X, and then momentum doesn't commute with the Hamiltonian just because there is also the boundary conditions that prevent that from happening. But now, since we are not constrained to the conserved quantities or operators that commute with Hamiltonian, we can consider particle in the box, and there we know the eigenstates, right? So psi, if it's 2 over L sine n pi x over L, then you could expect for any function like that, the expectation value of any operator time derivative to be 0. Okay, if again a is not time dependent operator. Well, position and momentum they fall into this category, right? So you could simply do like mathematical experiment if you want. Like if we look at what is the position of expectation value of the position will be for any function like this for the particle in the box, then it will be staying constant, whatever it was at the time 0, essentially, right? Because what's going to happen if you start with a psi x 0 to be, say, one of these eigenfunctions? Well, at later time, we know it should be with minus ent divided by h bar. And so generally, x at later time should be integral over dx. Here we have sine, well, technically psi xt star x psi xt. And that generally can have time dependence, but in this particular case, it doesn't, because this factor in the star quantity and non-star quantity, they cancel. That's another way to see that this is going to be constant, or whatever time you pick, it's stays constant. So we can pick the 0 time where there's no time. This just becomes a trivial one. Okay, so the same with the momentum, really. Any questions regarding this example? All right.
Just
so
to clarify, it's a psi star x comma t times psi x comma t, right?
no,
Yes.
this is x. This is x.
Oh, okay. And the other one is a t and and closed brackets, right? Left from that x.
Okay, so
Just because
this notation really is the expectation value of any operator, right? So that would be always the integration over space. You have psi star x at t at later times, at any time t, really, and then operator a acting on the psi x t, right? So that's the notation. And then what this means is just to say that the time here in this expression is just 0, right? So, and this is at the general time.
okay, yeah, I just couldn't read see if there was a separation between the symbols, if it was a bracket or not.
No, well, brackets, yeah, technically when I use brackets, there should be no axis or variables, essentially, because this bracket representation is like a coordinate-less representation. It's just the vector itself. It hasn't like the coordinate system is not defined, but this is a little bit more advanced, I guess, discussion. For this course, these brackets simply will mean the integrals, right? So, and that's why we usually don't write something like psi x psi x, because this is the part that is the integration, and this is not the right notation. If you want to write psi of x, really the right notation would be x psi. Okay, so
Okay.
but this understanding this kind of would require a little bit more of a discussion, which we didn't do, and so that's why I don't want to go too much into that. This is more sort of advanced stuff, but for us, this is not to be used. We use either this or the right thing to put there is t, because t is not a variable really, it's a parameter. So whenever we consider quantum mechanical system, we consider that it's at certain time. So all our functions or like a Hilbert space or vectors, they are in the spatial. They depend on the spatial coordinates, and the t is like they always consider that at a certain time, which is a parameter, and it's like a fixed. And if we want a different time, we just go to that different time and then consider everything there. And so the different times are just like a different slices of space, and they're not really connected with any like there's no Hilbert space or functional space of time. There is only functional space of spatial variables. That's why. But if you, I guess, don't follow completely this explanation, then that's okay. We will be using this notation, and this is just what we define by the brackets, right? So the integrals over space. Okay.
Right.
All right. So now the example. Let's consider a more chemically related example, I guess, for this situation where nothing should be happening, and yet things do happen. So let's say for the chemical reactions in many places, we could consider the reaction coordinate. And of course, in general reaction, like there could be multiple reaction coordinates. There are more than one dimensional changes that are happening in chemistry. Like there are many more coordinates, and that's why lots of them are sort of involved. But at a certain degree of simplification, we could always consider one dominant coordinate, and then the reaction usually between the two, say, states can go over some essentially barrier. That's why they happen in the not on a like a femtosecond scale, but femtosecond scale comes from the scale of the usual vibrations in the molecules, but they happen on a slower scale because there are usually barriers that separates the various forms. So it's quite realistic to consider that, okay, if you want to think about chemical reaction, there is a potential that depends on the space, and it has minima. For simplicity, we can think of this minima to be exactly the same. And to have chemical picture, we could use malone aldehyde. Let's say we have OH group here, and it's like this. It's malone aldehyde, and it has two tautomeric forms, which are separated by some barrier. Of course, because, well, it's more stable for the hydrogen to be close to the oxygen. Well, then, if we have two equivalent oxygens, it's still, they are separated far enough so that it's better energetically for hydrogen to be near one of them rather than being in between. So this, let's say, is a configuration A, and this configuration B, or this is reactant, this is product, if you want. And so this transformation kind of keeps happening, usually with some time scale. And we could been sort of separated somewhat from the experiment, say that, okay, we could create potentially the system in one barrier and explore how is it evolving in another barrier, right? So if we want to do that, we need observable, like in quantum mechanics, we need an observable operator A of some sort, whose expectation value will tell us how the reaction is going, like how far did it go. And so the natural candidate for the such observable or operator is the Heaviside function, which is, if you haven't heard about this very simple thing, it's a step function that is 0 before, like, let's say, for all the negative values and 1 for all the positive values, right? So let's say we have a origin of the coordinate system here somewhere, right? So these are all going to minus infinity, these are plus infinity, right? And so that's why A being the heavy side, h of x is simply 0 for x's that are negative and 1 for x which are positive or 0. Right, so that is the our observable, and if we place it so that our coordinate system is on the top of the barrier, right? So then we can use our expectation value for the Heaviside function to say that okay, our system is either on the reactant well or in the product well, right? So if the wave function is somewhat localized here in the reactant well, then clearly the psi square also will be in the reactant well. H of x, if you integrate from minus infinity to plus infinity, if this whole thing is in the region where it's negative x, then this becomes 0, right? So that means you are at the starting point. If things move into, say, here in the product, the function arrived, then in that case, we'll have this integral to be 1. Okay, so any questions about this setup? All right, so then tell me, what are the eigenfunctions of our operator and what are the eigenvalues?
Would it not depend on what function we're using as psi?
Eigenfunctions of operator they have no knowledge of your psi. Right, so operator has eigenfunctions and eigenvalues, and they have no idea about quantum mechanics. They have no idea about your wave function. They have no interest in what you're doing, what your system is, right? So they are by themselves, right? So what are the eigenfunctions of momentum operator? Has nothing to do with you. It's like they are just plane waves, exponential function of ikx, which if we differentiate, we get back the k, right? So has nothing to do with psi. And the question is, what are the eigenfunctions for the H operator? So H of x multiplied by phi n x equals lambda n phi n x. Well, here's a simple picture. What is h of x? It's function like this, where this is 0. It stays at 0 in the negative values of x negative, x positive, it becomes 1, right? So the question is, what are the functions? If you multiply by h of x, you get back the function multiplied by a constant, right? So the simple answer is anything that is localized in the negative region is an eigenfunction with the eigenvalue 0. And anything positive localized in positive region is an eigenfunction with the eigenvalue 1. If you have something that is between the regions, it's not an eigenfunction because it's going to be cut, right? So this part will be multiplied by 0. This part will be multiplied by 1. And so function will change its shape. Okay? So is that clear?
Yep.
Great. So then let's see. Okay, so if we start at with some initial wave function in the well, in the reactant well, is that eigenfunction of our operator?
Could you repeat if we what?
If we start with a wave function that is in a reactant well, localized fully in this region, is this eigenfunction of our operator?
It would, because as it would still be 0, but like if the eigenvalue is 0, then anything would just keep being 0.
It would be multiplied by 0 because it's localized and there is no really anything beyond the region, negative region of x, right? So then if the second question, if we end up with a wave function that is localized in the product, it's also an eigenfunction because, well, everything in this wave function is multiplied by our Heaviside function 1 value. So this is going back to the function itself multiplied by 1. So it's eigenfunction as well, right? So great. So what we have is the situation where we have observable A, we have a wave function initially that is an eigenfunction of A. No matter whether we start in reactant well or product well, our function is localized in that well, and then for our observable, it's an eigenfunction. That means, based on this consideration, that the time derivative and also, well, Heaviside function is a Hermitian observable. Also, it has no time dependence, right? So it's h of x, doesn't change with time. So therefore, the expectation value of our observable should be 0, which means if we start in reactant well, it stays in reactant well. If we start in the product well, it stays in the product well. So there's a clear contradiction we got with the fact that reactions actually happening, and you saw yourself in the simulations that I did a couple of lectures ago that if you put quantum system with a barrier and you localize system in one well, it will tunnel into another well, no matter how large barrier is, right? So technically, this expectation value should not be constant in time. Yet the Ehrenfest theorem says that the time derivative of our thing is our Heaviside function is 0. So any suggestion how to resolve this problem, to this contradiction? All right, so just to give you a hint, it's really not that different from classical mechanics. If the first derivative, let's say in classical mechanics, in the classical physics, how do you know that things are moving or not? If someone says that velocity is 0, you may think that things are not moving, right? Because velocity is, if you have a position, classical mechanics have position, then you need to have time derivative of the position, which is non-zero, to say that things are moving. You need to have velocity. Is this always the case? Can things start moving with 0 velocity? Sure, they can. If you drop something unintentionally, right? So the initial velocity of the object that falls is usually 0, right? So because you release the object, say, and under gravity, it just falls. So the fact that time derivative is 0 doesn't mean that things are not moving. It just means that velocity is 0, acceleration may not be. Because after all, movement is change in time, this quantity, right? So this quantity can be time dependent, and we usually, if it's a like any physical quantity which is continuous, well, then you have a Taylor series, and you could write it at a 0 time. That's a starting point, plus the whole Taylor series, meaning that it's the first derivative times t plus the second derivative, like the calculus teaches us, and so on. So divide by 2, and so on. So if you have 0 first derivative, doesn't mean that the second derivative is 0. Okay, so like in the case of falling objects, we have non-zero acceleration and 0 velocities. So here, the simple resolution of this paradox is there is a 0 velocity initially, but at later time it's not 0 because there is an acceleration. And if you continue differentiating like we did in Ehrenfest theorem and obtain the second derivative of A, that will not be 0 even for the state that is an eigenstate of the operator. Okay, so that's one way to think about it. Another way to think about it is that the fact that some state is an eigenstate of the operator doesn't mean that it's later going to be eigenstate of the operator, because all the functions, they evolve according to Schrödinger equation, right? So that's why being an eigenstate of H is so special, because if you are in the eigenspace in the eigenstate of H, then you stay in there, since things are evolving, but they evolving as an eigen, is in accordance with the Schrödinger time-dependent Schrödinger equation, and they stay stationary if you start with stationary. But if you start with eigen function of one operator, it may be at later time not an eigenfunction of that operator. Simply because the evolution will march on and things will change. Like in this case, very simply, we saw if you do the simulation, which means you do the calculations of the evolution of the wave function at later time according to Schrödinger equation. Well, there is a tunneling, and then the system appears on the other side, right? So while it's doing that in the middle of that process, it's not, of course, an eigenfunction of H, but it goes between being eigenfunction of H in one well, being eigenfunction of H in another well. All right, so all that is to say that these two cases where the where the Ehrenfest theorem says that time derivative is 0. And there are two subcases. One is where wave function is an eigenfunction of h, and where the wave function is the eigenfunction of a. They are very different because of the special role of time-dependent Schrödinger equation. So for this case, things will stay the way they were found because the wave function is an eigenfunction of h. But for this case, it's not necessarily static situation, because at later time the function may change from be an eigenfunction of operator to not be an eigenfunction of the operator due to the time evolution. Okay. Any questions?
So also due to time evolution, you could an eigenfunction could theoretically go from being an eigenfunction of h to an eigenfunction of a, or vice versa. Or if it's an eigenfunction of h, even due to time dependency, would it stay or just not change to being an eigenfunction of a?
Due to time-dependent evolution, function that was eigenfunction of h, it's a stationary state, right? So it cannot change being the eigenfunction of h, right? So it's sort of being eigenfunction of h is forever, okay, in quantum mechanics. It's easy to see because we saw that for any wave function, the time evolution is always a linear combination of eigenfunctions of h. These guys are eigenfunctions of h. Right, so if you have a situation where you have your function be an eigenfunction of h, that means only one component here should be non-zero, right? So your function should be like this. It's a eigenfunction. It has a it's a stationary state, right? So this is your function that is an eigenfunction of h. If you have more than one components, they are not eigenfunctions of h. Okay. And so then this function could be eigenfunctions of some other operators, so may not be eigenfunctions of other operators. It's like depends on whether h commutes with those operators that you're considering. Say, in case that if they commute, then maybe, as we saw. But yeah, that's the kind of the situation. Being eigenfunction of h is for forever. Being eigenfunction of some other operator may not be forever, because if you have a function that is an eigenfunction of some operator, it doesn't prevent that function to be a superposition of eigenfunctions of h. And if that's a superposition, then it will always evolve. And when it evolves, like evolution in time is determined by these coefficients. And these coefficients, they oscillate. So they can make some contributions large and some contributions small in different time periods, right? So essentially, that's what is going to happen. So at zero time, this psi of xt could be an eigenfunction of some operator, but at later time, it's not. Okay. Does that answer the question?
Yes.
Okay, good. So always remember that the wave function, if you are interested in the dynamics of quantum system, the easiest way to figure this out is to just write down the wave function as a linear combination of eigenfunctions of the Hamiltonian. right? So these coefficients, the only things, well, if you know the eigenfunctions, the only thing you need to know is the coefficients, and they obtain like integrals. Conceptually, that's straightforward. It's just decomposition of one vector in basis of other vectors, using inner product to find the coefficients. Or Fourier decomposition is another name for the same thing. And then you kind of just add this time factors, and you obtain the evolution. And that's it. So sort of once you have the wave function at any time, you could predict what will be the property of any operator by taking expectation value of this function with the operator. And then you could see that whether expectation value is the same or not. Ehrenfest theorem just tells you about the first derivative. That is usually enough to say, all right, that this first derivative showed me that it's sort of things will not change in time because the first derivative is 0, but that is sometimes tricky because it's subject also to the question whether the second derivative is 0 or other derivatives are 0. So in some cases, we obtain the first derivative is 0, and that's enough to say that, okay, things it will stay 0 and will not change. But in some other cases, it's not that simple, right? So one needs to be more careful.
So on that note, should we always, if we get a first derivative at 0, should we always verify if the second one is 0 or non-zero? Or for the sake of this course, if it is 0, we just state that it stays.
Yeah, you could either go for the second derivative, or you could just understand where dynamics can come from, right? So the dynamics, usually the change can come from the evolving wave function. So if the function is stationary state, it's not going to evolve anywhere. If the function is non-stationary, then you may have a situation then that there will be evolution of the first derivative and other quantities. So usually in order to have a conserved quantity for the non-stationary state, then you need to have non-zero commutator, right? So if your state, you could formulate the rules that if your state is non-stationary, it's like this, non-stationary state, then this needs to be non-zero for the dynamics to happen, right? If h of a commutator is 0, that's the only way to make sure, to have null dynamics for the quantity, right? So there is, after all, kind of reason for the dynamics of this quantity is the evolution of the wave function, right? So if it's in order to have evolution of the wave function, it needs to be non-stationary. And then if it's non-stationary, then the question is whether the quantity you are considering is commuting the Hamiltonian. If it does commute, then there will be no change in the kind of the expectation value. But if it doesn't commute, then there will be change. Or you could just simply look at this quantity and plug in the wave function in this form and see what's gonna happen, like how many integrals do they depend on time or not. Because you can always do that. Simply just write if we have a psi xt, right, the integral. Let me carefully write it. psi x t star dx a psi x t, right? You can write this by writing the wave function, if it's non-stationary, as a linear superposition. So we'll need two indices, one for this guy and one for this guy. So this is Cn star, Cn, and then have phi n prime, phi n star a, phi n prime x dx, here the same x dx, right? And what else do we have? We have the minus e n prime t divided by h bar, and plus I e n t divided by h bar. So what this will be, sum over n prime, and let's call these guys, so just phi n a phi n prime, right? So then we'll have them. Let me just write it clearly again. And here we'll have en minus en prime t divided by h bar, and the coefficients, right? So Cn star, Cn prime. So what this tells us is, you see, if we have a linear superposition of Hamiltonian eigenstates as our wave function, which is non-stationary state, then the evolution of the expectation value of the operator will happen if we have n non-equal to n prime terms, because these terms have these exponential functions with the non-zero coefficients before the time, right? So this delta energies, they come from this n non-equal to n prime. Okay. Of course, that if imagine the situation where Fn is an eigenfunctions of A, so they both eigenfunctions for the Hamiltonian and for A. So then all the n equals non-equal to n prime parts, they will just be zero, because if we have this condition, then phi n a phi n prime will turn into delta n n prime a n, because this is from the phi n prime, right? And this is from the fact that a, when it acts on the one of those functions, it gives you eigenvalue, right? So then, since we have a delta, all the off-diagonal terms will disappear, and there will be no time dependence. But you see, what we required for that is that A shares eigenfunctions with Hamiltonian, which is another way to say that A is commuting with Hamiltonian if it shares. Right, so we got the consistent result that if we have if we have a H commuting with A, then even in the situation where our function is non-stationary, there is no dynamics, because simply you will have absence of the off-diagonal terms. By the way, these terms also called coherences. So these off-diagonal terms, that's what results in the dynamics. But as you can see, all that you could just do by yourself, right? So thinking of this as like a rule is not necessary. You could just do the sort of little algebra that is quite straightforward, knowing that, okay, if they have an eigenfunction or not, that's all you need here. And I hope that's clear. Now, do you have any further questions?
Oh, clear.
All right, great. So we didn't get to the time energy uncertainty principle, but I guess I'll start the next lecture discussing that because it's something that you may hear about, well, in the context of quantum mechanics. Okay. All right. See you on Wednesday.